So,
I'm not sure.
oh, you guys need to see.
Mine is really feel like Calc, so it's 6 points.
How long is our first semester? And then we had that conic section.
Yeah.
That was a lot of guess and check. Not a lot of guess.
All right, so we're going to talk about parametric surfaces.
Mine was
So we have, this comes up, there we go. So we've talked about parametric, we've talked about parametric equations of curves, both with parametric equations and with vector value functions. And we're going to do something similar with surfaces. And what this is going to lead us to, we're going to take this idea of a parametric surface, and we're going to do a surface integral. So we're going to sum the normal components of a field over a surface. So we want to build the tools that we need to do that. So when we write curves in parametric equations, we usually use a single parameter t was our normal parameter, t, theta, something like that. When we have a parametric surface, we end up parameterizing our surface with two variables. So let me just, as a quick reminder, for curves, we had several ways to represent them. We could represent them in explicit form. An explicit form is when we have y equals f of x. And then we could have an implicit form. And that's when we have some f of xy equals 0. And then our parametric or vector form so when we talked about those, we had our t is x of ti hat plus y of tj hat. Surfaces, similar thing for surfaces. We've worked a fair amount with the explicit form of surfaces. We had z equals f of xy, and we also worked with the implicit form, where we had f of xyz equals 0. And now we're going to talk about our parametric form today. And that looks like we're going to have an r of two variables, u and v. And we have some function of u and v I hat plus some other function of u and v j hat plus a third function of u and v k hat. And f, g, and h are continuous functions on some domain in the uv plane. So our surface r of u and v is our parametric surface, and the f, g, and h are parametric equations for the surface. And on the cover of our textbook, that is a parametric surface, and I have the parametric equation written along the spine there. That's a pretty complicated parametric equation, actually. So just like in the plane, parametric equations for surfaces aren't unique. And to sketch or to visualize what the graph of a parametric surface is going to look like, we want to try to eliminate the parameters, just like we did in the plane, or we want to look for some relationship between the components, some way to relate the x, the y, and the z components. Um, Finding parametric equations for surfaces is usually pretty difficult. We just have a surface and we want to write a parametric equation for it. Kind of difficult. The exceptions are we're familiar with cylindrical coordinates and spherical coordinates. That's one way to parameterize a surface, is with those coordinates. So we're familiar with those. And if we have our surface in explicit form, we have z equals f of xy. Our parametric form would be x I hat plus y j hat plus f of xy k hat. And that would be a parametric. That would be a parametric representation of this surface z equals f of xy. So cylindrical, spherical coordinates, and when we have our surface in explicit form, we can always write it this way. And for the most part, we're going to be working with surfaces in one of the other of those forms, so we have an idea of what we're dealing with. So what I want to do first is take a look at some graphs of surfaces and match the surfaces to their equations, and take a look at how we eliminate the parameter find relationships between the x, the y, and the z component. So questions so far? All right. So let me grab this. So there are our graphs. And I'll put the equations next to them. Came out a little more clear in the PDFs. All right, so for number one, we have R of u and v is ui plus vj plus uv k hat. And we want to match that to the surface. Any ideas there? So I look at this and I say, let's find a relationship between the components. So x, so this is like what I wrote back here. This one. How is z related to x and y? Z equals xy. So that would be the explicit form of that surface. So what surface is going to be z equals xy? What is xy? Z equals xy. Xy equals say xy equals 2. What kind of graph would that be in the plane?
Just go on.
Is it a line?
Z equals 2.
What's that? So what if we looked in the so we're in xy plane, we have xy equals a constant. X times y equals a constant. So x would be y equals some c. So let's say xy equals 2. So x equals, or let's say y equals 2 over x. What is y equals? Let's make it even easier. 1 over x. What's y equals 1 over x? Does that look like? No? Inverse function. So that gives us hyperbolas, right? To get something like that. So which one of these surfaces has hyperbolas? E. Right? We get hyperbolas along this way. So we have hyperbola this way. So that would be E. How about number 2? So we have u cosine v I hat, u sine v j hat, and u k hat. So Josh says D. And what makes you say D?
Because that's cosine plus sine.
Okay. So there's some kind of, we know when we see sines and cosines, we think of some kind of relationship involving the Pythagorean identity. So let's square the x and the y. X squared plus y squared equals u cosine v squared plus u sine v squared. So that's going to be, I factor out a u squared times sine squared v plus cosine squared v. And u squared is z squared. So we have x squared plus y squared equals z squared. And what is that? That's f, a cone. So this would be f. So you're on the right track, Josh? That there was a relationship, that relationship was there? It was just that it ended up, the z squared ended up on the wrong side of the equation, the sphere. How about number 3? So what's a relationship between u and v here? Or x and y and z here? Y equals 1/2 x plus z. And what is that? Linear in x, y, and z, so that's going to be a point. So that would be number, or letter B. Yeah, not too bad. When we have nice relationships between our variables. How about number 4? 8? Is that you, Dylan?
Yeah.
So what makes you say 8? Have the cubic. So we know that y equals 1/4 z cubed for any x. So that would be 8. Let's look at 6 and then we'll look at 5. So number 6, we have, and I think this 6 would be the D, because we'd have x squared plus y squared. Would it be C? Let's take a look. X squared plus y squared equals 16 cosine squared u plus 16 sine squared u equals 16. So our surface is x squared plus y squared equals 16 for any z. So what is that one? That's C. That's a cylinder. Almost. We've almost got to the sphere now. So that's why I want to do this one last. For number 5. So let's look at how we would deal with number 5. So we have an idea. We have an idea that x, y, and z are related somehow by the Pythagorean identity. So let's do that one.
Does
So
the fact that there's cosines and sines in every part of the IJK indicate that it's somewhat spherical?
it depends on the relationship. It depends on the relationship between those. What's that?
They're exactly right.
Yeah, so these turn out to be, this turns out to be our transformations for spherical coordinates, right? X is sine, is rho
Looks like
sine phi cosine theta.
looks like a row is
Y is cosine phi sine theta. And Z is rho cosine phi. So this is the transformation to spherical coordinates. So this would be a sphere. And we could square the x component, square the y component, and we'd end up with x squared plus y squared plus z squared equals 2. So that would be a sphere, or equals 4, radius 2, I believe. So number 5 turns out to be our sphere D. So we could recognize that this is spherical coordinates. These, instead of rho, phi, and theta, I used V and U, but this is exactly spherical coordinates.
So it's not cosine V, it's sine V.
Are they switched around?
Oh, it is sine V for the K component.
Oh, the K component?
So it's like spherical coordinates.
Like spherical
except
coordinates.
it's coming out of the axis.
Right, right. And what we would do is we would square this term, square this term, square that term, and we see that x squared plus y squared plus z squared equals 4. Because the term here, the cosine u and the sine u, when we square those end up being able to be factored out, and we can ignore those. And we just have the cosine v's and the sine v's involved. All right. So let's look at a couple more examples where we're just looking at the equations and not worrying about the surfaces. So I just want to work a few of these. So we want to find the rectangular equation. So we're going through the same process. We just don't have the surface to look at. So let's say our R of U and V is Ui hat plus Vj hat plus V over 2 K hat. So this one's pretty easy. What's our relationship here between the components? Z equals y over 2
For any x?
for any x. So we could say 2z equals y, or 2z minus y equals 0, and that surface would be a plane. How about R of U and V is 2u cosine V plus 2u sine V plus 1/2 u squared. This should be an I hat, a j hat, and a k hat. So what would we want to do here? Square the I and j. So x squared plus y squared is going to be 4u squared cosine squared v plus 4u squared sine squared v, and that equals, that's going to give me 4u squared. So x squared plus y squared is 4u squared, and 4u squared is 8z. So we get x squared plus y squared equals 8z, and what is that thing? Parabola. All right, now let's look at one more of these, and then we'll do something a little different. R of U and V is 3 cosine V cosine U I hat plus 3 cosine V sine U j hat plus 5 sine U k hat. So again, we're going to want to square the x and y component. So when we square the x and y component, I get 9 cosine squared v, and I get a cosine squared u and a sine squared u that we can factor out. So that just gives us 1. So we get x squared plus y squared is 9 cosine squared v. So how are we going to relate the x squared and the y squared to the z component now? Let me do this. X squared plus y squared over 9 equals cosine squared v. Cosine squared v is, did I write this right? This should be a cosine. There we go. That should make more sense now. X squared plus y squared over 9 is cosine squared v, and cosine squared v is z squared over 25. So then we get x squared over 9 plus y squared over 9 minus z squared over 25 equals 0. Is that what I wanted to do? I don't think so. I wanted to leave this as a sign. I want to leave that as a sign u. And I want to erase all this other stuff. And make this bigger. So this one, I want this one's going to be a little bit trickier. So now we want to relate the cosine squared v to the z component. So it's add z squared over 25. So I'm going to say x squared plus y squared over 9 plus z squared over 25 equals cosine squared v plus sine squared v, which is 1. So we end up with x squared over 9 plus y squared over 9 plus z squared over 25 equals 1. And what is that? And ellipsoid. So this one a little trickier, but still not too bad. All right, questions there? Okay. Now I have a couple of questions for you. Let's say we start with the surface. We have a parametric surface R of u and v, and we get u cosine v I hat plus u sine v j hat plus u squared k hat. And we have a graph of this function over some interval. I want to know how the graphs of these following surfaces, the next surfaces that I write, are going to be different from the graph of this surface. So let's say we have S of u and v is u cosine v I hat plus u sine v j hat minus u squared k hat. How would the graph be different?
Would be mirroring across the XY plane.
So we reflect it. This would be reflected in the xy plane. Everything's the same except our z's are negative. So this is going to reflect in the xy plane. Or to say it flips over. And before we go on, what's our relationship here between our x, y's, and z's for this surface? If I square the x and the y, I get x squared plus y squared. I get a u squared cosine squared v, a u squared sine squared v. So I end up with x squared plus y squared equals z squared. Or z. X squared plus y squared equals z. So this is a, what kind of surface? Paraboloid. And what's our axis? Z-axis. So our z-axis is our axis. So for this next one, we have S of u and v is u cosine v I hat plus u squared j hat plus u sine v k hat. So how will this one be? How will this one be different? This would have the y-axis as the axis of our paraboloid, because we'd have x squared plus z squared equals y. So our axis of symmetry would be the y-axis. Now what if I told you that this was for 0 less than or equal to u less than or equal to 2 and 0 less than or equal to v less than or equal to 2 pi. And for this one, I'm going to say our surface S of u and v equals r of u and v, where we're going from 0 less than or equal to u less than or equal to 3, 0 less than or equal to v less than or equal to 2 pi. What would be different here? It'd be taller, right? So we're letting z would be bigger. This would be taller. And what if I did for the last one? What for the last one I said S of u and v is 4u cosine v I hat plus 4u sine v j hat plus u squared k hat. Wider. Our circle will be bigger. Right? So this would be wider. Our parabola would open up more widely. All right, questions there? All right, let's do a couple where we go the other direction. So we want to find a parametric representation of these surfaces. So a vector value function. For the surfaces, for these surfaces. So we want the plane, x plus y plus z equals 6. We want a vector value function. We want to write this surface in parametric form. So what do we want to do here?
Can we make XU and Y?
We could make, and we could make XU and YV, or we could make it even simpler, but let's do it that way. X equals U, Y equals V, and then how are we going to represent Z? Z equals 6 minus U minus V. So our vector valued function, R of U and V, our parametric form, would be UI hat plus VJ hat plus 6 minus U minus VK hat. And we could have left our parameters just as X and Y and just written this as R of X and Y and done the same thing.
Is there any easier way to do this?
No. That's about all we can do with that one. How about 4x squared plus y squared equals 16? Have to do a little more work with this one. What do we want to do first? Let me do one step here. So I'm going to divide everything by 16. So x squared over 4 plus y squared over 16 equals 1. So what does that suggest? We have an x squared and a y squared and equals 1. So it's a cylinder, and when we have the x squared and the y squared and that equals 1, that suggests sines and cosines. So how about x equals 2 cosine u and y equals 4 sine u? So x squared over 4 plus y squared over 16 equals 1. And z can be anything, right? Since this is a cylinder, elliptical cylinder. So z equals v. So our parametric surface, R of u and v, is going to be 2 sine u I hat plus 4 sine u j hat plus v k hat. 2 cosine units. There we go. And that would be a parametric representation of that elliptical cylinder. So what we're going to do with these parametric surfaces tomorrow is take the parametric surfaces and use this representation to come up with use this parametric representation to come up with a representation of the little surface area element ds. And then we're going to use that surface area element, and we're going to eventually start working with the vectors, our vector field on the surface. We're going to be summing components of vectors over these surfaces. And we'll come up with a three-dimensional kind of analog to the two alternate forms of Green's theorem that we talked about. We talked about the tangential component. Summing the tangential component around the boundary was the normal component of the curl over the region, and the outward component of the field around the boundary was the divergence over the region. So we're going to come up with three-dimensional versions of those two ideas, and that'll be the divergence theorem and Stokes theorem. All right, homework. go.
Because we did subtract.
Well, we're gonna